Hello, everyone. Welcome to another probability stat interview session. So today I'm going to cover maybe 3 questions if time permits. So for your information, we are planning to continue with these programs. As Dr. Badai said, we will be very happy to hear your feedbacks, your reviews, and we encourage you guys to give us some reviews. Okay, so I'm going to share the notebook that I'm going to be using today with those who post a review with us for us. Okay. All right. So let's get started. I'm going to share my screen. You don't have to have any file. I'm going to post a question, and then you can simply use an empty Jupyter notebook. If you don't have Jupyter notebook, you can simply use your Google Colab. So what I'm going to do is, as I did before, I'm going to try to solve the question first, if possible, mathematically, and then I'm going to use Python to run some simulation to solve the problem. Today, I will continue with probability questions. Maybe as we move forward with these sessions, I will start talking about A/B tests, hypothesis testing. So I have a lot in my list, actually. On my list, but let's see. Let's continue now. I'm going to share my screen. Okay, where is it? So I hope you can see my screen, right? Okay, and thank you. For the questions, if you could please post your questions on the Q&A section, so I can see your questions, because on the chat, so there are a lot of things posted at one time, so maybe I may miss your questions. Yeah, so again, I'm gonna give the copy of the code today if you can post a review for us. Okay, so that's the condition. All right. So let's continue. If you remember, last time we were done with the first 2 questions. Now the third question. Here is the third question. So let's see. A miner is stranded, and there are 2 paths he can take. Okay, so it's a bad situation. So there are 2 paths he can take. Path A loops back to itself and takes him 5 days to walk it. Okay, so he's stranded. There are 2 paths in front of him. The path A takes him back to where he started, and then that takes him 5 days to walk. So path B, so here is, let's say this is the starting point. Okay, if he takes path A, he comes back to the starting point. Okay, and this takes 5 days. Okay. So path B brings him to a junction immediately, and this time there is no waiting time, so it takes only 0 days. All right. And then there is this junction at the end of path B. There are 2 paths, BA and BB. So this is his starting point. If he takes path B, this takes him immediately to a junction point. Okay. And then there are 2 paths. It's either BA or BB. Let's say he takes the path BA. So if he takes the path BA, and then path BA brings him back to his original starting point, okay, where is S, okay, and this takes him 2 days to walk, okay, 2 days. So again, from the starting point to path B, there is no time gap, right? So it takes only 0 days to take path B, because it immediately gives him a junction. If it takes path BA, it again loops him back into his starting point, which is 2 days, okay. And the other way, again, starting point. So he is taking path B. So he's not taking path A, but path B. But this time, from path B, he's taking path BB. Okay. So the path BB brings him back to safety. Okay. Let's call safety T. Okay. So if he takes path BB, he goes back to safety, and this takes him 1 day to walk. Okay, perfect. So 1 day. All right. So this is the description of the problem, right? So there are 2 options, A or B. A takes him back to the starting point. B, 2 junctions. BA takes him back to starting point. BB takes him to the exit. Okay. All right. We understood what is going on. So each path has an equal probability of being chosen. So this is important. So at the junction of path A and path B, it is equally probable, okay, going to path A or path B. And at the junction path BA and BB, again, it is equally probable to go to BA or BB. So 0.5, 0.5, 0.5, 0.5. All right. And the second piece of information which is important, once a wrong path is chosen, right? Once a wrong path is, what is the correct path? BB, right? So he has to first choose B and then BB so that he can get to the exit. But once a wrong path is chosen, that means once he loops back to his starting point, he gets disoriented and cannot remember. It's memoryless. So he doesn't remember, oh, at the beginning I chose path A and then that's why I came back to the starting point. So let's assume that he doesn't remember. Okay, so everything is refreshed. Okay, so he gets disoriented and cannot remember which path he went to. That means every time he starts, it's a fresh start. All right. So what is the, under these conditions, what is the expected value of the amount of days he will spend before he exits the mine? So when somebody asks you this question, of course, they're not going to give you all these explanations. So the explanations I try to give you actually are either you think and then speak loud, right? Or you will ask these clarification questions to make the problem clear to you, right? So I think now the problem is clear to us. So now let's solve the problem, right? So as I said, I'm going to solve the problem first. Let's try to solve it mathematically. And then if possible, let's do the, what is that? Simulation. Okay, simulation means I'm just going to write some Python code and then I'm going to verify what I thought what I thought I got the solution mathematically. I'm just going to verify my solution. All right, so to approach this problem, actually, the problem is very simple, but to approach this problem, let's first of all take one cycle. So let's say that each time the miner, right, starts from the starting point. Each time he starts from the starting point, either coming back to his looping back to his starting point or taking the exit. So let's call this one loop. Okay, one loop. All right, so that means if you consider his journey as one box, from one side of the box he enters, okay, from the other side of the box he either exits the mine or he goes back to the starting point, right? So this almost gives you that each time he starts his journey, okay, to the exit, it is either he exits or he goes back to where he started. Okay, so there are two options, either he exits or he goes back to where he started. So if you remember our previous discussion, which happened 2 weeks ago, if you don't remember, it's okay. So this is almost like each time he is trying to do something, right? And that there is a certain probability of achieving that. That means finding the exit, or there is a certain probability not finding the exit, right? So he either finds the exit or he doesn't find. So he's gonna maybe take path A, or he's gonna take path B and then take AB, but eventually he's gonna come back to where he starts. So there are two outcomes. Either he's gonna find the exit or he's not going to find the exit. So every time he starts, it's a fresh start. It's almost like flipping a coin. Think of this as a flipping coin. So we are going to flip the coin until, let's say, we get the tail. So each time we get head, we are going to flip it one more time and then one more time. So the question is, how many times it's going to take us to get our first tail? Okay, so if I ask this question this way, okay, so you start flipping a coin, and then let's say the first time you flipped, it is head. The second time it is head, the third time it is head, and the fourth time it is tail, and then you stop. Okay, let's imagine this is such a problem. So in that case, as you remember from our previous discussion too, this is nothing but, again, geometric distribution, right? So the number of trials it takes for us to get the first tail, okay, let me write it, the number of flips it takes us to get the first tail, right, is a geometric distributed random variable, right? Okay. So again, remember from our previous discussion, so if probability of tail is P, which is the success probability, this is the way we define success. Probability of tail is P, and if this is a fair coin, it is 0.5, right? So in that case, expected number of, let's say number of flips, I'm going to denote it as N, okay? So expected number of N is nothing but 1 over P. Okay, so again, if you ask me, oh, why is it 1 over P? So we can mathematically show that it is 1 over P. It's not a big deal, but it is 1 over P. Again, what is P? P is the success probability. Okay, so this information, we now, as we are trying to solve this problem, we are thinking about using geometric distribution. Okay, let's go back to our problem. And there is but the probability of HT compared to exit, not exit, is not the same. Isn't it more probable than they will not find exit? Ramia is asking, the probabilities are not the same? Definitely. So here, so when I'm talking about flipping a coin, I assumed it's a fair coin. It may not be a fair coin too. So let's say the coin is not fair. The probability of tail is 0.3. The probability of head is 0.7. So in that case, the number of times it takes us to get to, so let me write it here. Let's say probability of tail is 0.3. That means the coin is not fair, and getting the tail is less probable. So our common sense says that it's going to take longer for us to get to the first tail because probability of tail is lower than 0.5, right? So that's why 1 over 0.3 is greater than 1 over 0.5. That means if the 0.5, if the coin is not fair, it's going to take longer for us. Again, an unfair coin, and then tail probability is lower, then it's going to take longer for us, or more number of trials for us to get the first tail, right? So it doesn't have to be the same probabilities, but the more important thing is this: each time I flip a coin, the outcome is binary. It's either tail or head, okay? And then I know the success probability. In this case, success probability, I noted as P. So let me see. For success, it seems you need even number of attempts. So the first success probability seems to be, yeah. Now we need to, so that's why I said, let's assume that when he starts his journey to the outcome, let's imagine that as a box. And then this box is going to give us a success, which is finding the exit, or failure, which is finding back to, or looping back to the starting point. So in that case, what is the probability of success? So in this case, what is the probability of, finding the exit? So let's go step by step. So first of all, what is the probability of A? Right, so he is at the very beginning, he has to find A or B. What is the probability of A? So the probability of A is, again, the probabilities are equal, right, at any junction. So probability of A is 1 over 2. Then what is the probability of B? Right, probability of B is also 1 over 2, because A and B, the probabilities are the same. Once he chooses to go to B, then what is the probability of BA? So probability of BA. Now I'm using this given B, right? Probability of BA given B. Given B means given that he chose to go to the path B, what is the probability that he's going to choose path BA? Again, BB or BA, the probabilities are equal, right? So this is also 1 over 2. And then what is the probability of him choosing BB, given he chose B? It's again 1 over 2. So in that case, the probability of success, probability of finding the exit, or you can call it or success, is actually probability of BB, right? So if he finds the exit, that is success. Yeah. So yeah, Jeffrey is giving the yeah. Thank you for the answers. Yeah, you guys are giving me the answers. I'm right now. I'm using the notation to make things clear. Thank you for your feedback. So then, probability of BEB is probability of I'm writing mathematically. Okay, probability of BEB given B. First of all, he needs to choose B, and then once he chooses B, then he's gonna choose BB, right? So then probability of BB is probability of BB given B times probability of B. So this is a Bayesian equation, right? And this is nothing but 1 over 2 times 1 over 2, which is 0.25, right? So that means his success probability is 0.25. His failure probability is 0.75. So again, think of one cycle happening inside a box. The box has two outputs, either exit or looping back to where he started. So probability of exit is 0.25. Looping back to where he started is 0.75. Looping back is a little bit more complicated, right? It's going to be either choosing A or choosing B and then choosing AB, right? So there are two options for looping back. The combined probability of these two is equal to 0.75, but we are interested in 0.25. If probability of success is 0.25, then expected number of cycles or loops is 1 over 0.25, which is 4. So in other words, on average, in 4 trials, this person is on average after 4 trials or at his 4th trial, he is going to be able to find the exit. So that's what it means. That is what it means. Okay, but we are not done yet. So we only found how many trials it takes for this person, or how many on average loops it takes for this person to find the exit. It takes 4 loops. Again, that means 4 times he's gonna go inside that box, 4 times on average. And the 4th time he's gonna find the exit. Okay, now we need to find out what is the question? What is the expected value of the amount of days? So they're not asking about number of trials, number of loops. They're asking expected number of days. Remember, if he takes A, it's going to take 5 days for him to loop back. If he takes B and then from there BA, it's going to take 2 days for him to loop back. If it takes B and then BB, which is taking him to the exit, it's going to take 1 day to get to the exit. So each choice has a certain number of days. So we did not consider that yet. So we are still outside the box. So we are saying he's going to enter into the box 4 times. Now inside the box, right? How on average, how many days he's going to spend inside the box? So then this part is easy, right? So if he takes A, he's going to spend 5 days. Then what is the probability of taking A? 1 over 2. Then what I'm going to do is I'm going to multiply 1 over 2 by 5. So this is on average how many days he's going to spend. So if he chooses to go in the direction of A. Now we are in the box, okay? Plus, of course, that's not the only thing. A is not the only. So then if he chooses to go to BA, now BA is, first of all, he needs to choose B and then BA, remember? So that is 1 over 2 times 1 over 2. Now we are at BA. And if we choose to go to BA, it's going to take 2 days for us to loop back to where we started. So we're going to multiply this by 2. Okay, plus. Now we're not done yet, right? So there is this third option too. So again, if he chooses to go to B, which is 1 over 2, and then from B, if he chooses to go in the direction of BB, which is again 1 over 2, so that is the probability that he's going to choose the option BB eventually. So if he chooses the option BB eventually, it's going to take 1 more days for him to get to the exit. Okay, so as you see, 5 days for choosing A, 2 days for choosing B and BA, and 1 day for choosing B and BB. So this total amount is on average, inside the box, how long he's gonna stay. Okay, so what is this? 1/2 times 5 plus 1/4 times 2 plus, again, 1/4 times 1. So if you make the calculation, what is it? Anyone? I think it's 3.25, right? Isn't it? 2.5 plus, what is that? 3.25. Thank you. Yeah, I also have 3.25. So inside the box, he's going to be spending 3.25. Thank you. Thank you guys for the answers. Okay, that means each loop on average is going to take 3.25. We also found how many loops on average it's going to take for him to try to find the exit. Then we're going to multiply expected number of loops by, so this is days on average he will spend in one loop. Okay, so and then on average he's going to take 4 loops, so we're going to multiply these together, right? 4 times 3.25, right? So this is on average how many days it's going to take for him to find the exit given these conditions. 13 days. All right, so I hope this part is clear to you. So let me know if you have any questions up to this point. Now what I'm going to do is I'm going to try to find the same result or verify this by a simple simulation. Any questions up to this point? What if we do not remember expectation formula of the probability distribution being used? So that's something you need to, so then you, mathematically you need to then find it out, right? So this is, where is it? It is, again, let's go the example of head, and then tail. So how many times it's going to take for us to get to T? So for that, I mean, each trial is I mean, head or tail. So there is this probability of 1/p, and then we are doing this n times, and then you're going to take the limit. It's going to give you 1/p. Okay, so mathematically you can do this, but I don't suggest doing that. You just should remember it. Okay, for geometric distribution, it is 1/p. Okay, so now let's do this. And another option, if you don't remember the formula, is doing simulation. Okay, you can simulate it. Okay, so let's do the simulation. Now what I'm gonna do is I'm going to just write the code for for imitating that things are almost happening in reality. Okay, so what I'm gonna do is I'm going to make a person repeat the same procedure 1,000 times. Okay, so for that I'm going to use uniform distribution. Again, remember from our previous discussion, and also I'm going to use uniform distribution. Other than that, I think that's it. I'm going to use uniform distribution. So let's begin. First of all, I'm going to say I will repeat this 1,000 times. Okay, and then for 1,000 times, here is what I'm going to do. For I in range of T for 1,000 times, okay, what I'm going to do is I'm going to pick a random number. This random number is going to come from uniform distribution. So for that, let's import uniform distribution from scipy.stats. I'm going to import uniform distribution. So why am I doing this? So this is the way I am going to simulate it, right? So when you make a binary choice, right? So there are 2 outcomes. We simulate this situation with a uniform distribution where the random variable is between 0 and 1, right? So we pick a random, actually, it's not a random sample. So we pick a sample from a random variable, uniform distributed random variable, which is giving us a number between 0 and 1, and between 0 and 1, picking that number is equal probable, okay? Picking 0.2 or 0.5 or 0.7 is the same. That's why it is called uniform distribution. So if you want to simulate this binary choice situation using uniform distribution, what we are going to do is, let's say you pick A, okay? So let's make this even XA, okay? So let's say you picked XA, number XA, which is between 0 and 1, okay? So what you're gonna do is, depending on the probability of each event, so if binary choice, so there are two choices, let's say head or tail. So let's also note this in here, head or tail, okay? So, and then I'm simulating the probability that I'm gonna pick head, okay? I'm flipping a coin, the probability that I'm simulating the case where my coin is going to give me head. So I'm gonna pick a number between 0 and 1, okay? And then somebody also tells me whether this coin is fair or not. Or in other words, somebody's gonna tell me that probability of head is 0.7. Let's say this is not a fair coin. Probability of head is 0.7, okay? So I'm simulating this. So how I'm going to simulate this? I'm going to pick a number between 0 and 1, and that number is a sample from a random distribution, uniform distributed random variable, which is between 0 and 1. If XA is, greater than or equal to 0.7, right? So the probability of, probability of picking head is 0.7, right? If this number is greater than or equal to 0.7, I will assume I picked, if this is less than 0.7, less than or equal to 0.7, I picked head, okay? If it is greater than or equal to 0.7, so that means 30% of the chance that it's gonna be greater than 0.7, and 70% chance that it's going to be less than 0.7, right? So 70% chances for head, 30% chances for the tail, right? So that's how we are simulating. So let's do this here. I'm going to use uniform distribution. And what I'm going to do is, as long as, so let's say this is the number that I will be picking, and then let's give an initial number to this, ZB equals 0, okay? So while ZB is less than 0.5, okay, while this is the case, let's make this inside the parentheses so you know it is ZB is less than 0.5. I just want to emphasize it. So as long as this is less than 0.5, so what does that mean? So remember how we started. We are going to pick one of the A or B, right? One of the two, A or B, all right? And then as long as, if it is B, then we are going to pick AB or BB. And then if it is BB, then we are going to go outside, exit, right? So that means there are two choices we are going to make, A or B and AB or BB. So there are two random variables that we need to compare, okay? There are two uniform distributed samples. There are two samples from uniform distributed random variables, one for A and B and one for AB and BB. That's what I'm gonna do. Let me first very quickly write the code, and then I think it's going to be much more clear. So I'm going to make one sample, take one sample from uniformly distributed random variable, which I imported from SciPy stats. Okay, so this is RVS. Let me show you what happens when I do this. Again, I'm not making any assumptions on how much you know about Python or these libraries. So I'm assuming that our knowledge is limited, okay? So if you are already familiar with all this, sorry about that, but I'm assuming that we are all new into this. So I'm using uniform distribution from SciPy stats module, and I am taking one sample from this uniform distribution. So each time I run this, just 1 second. Each time I am running this code, it's gonna give me a different number, a random number, right? A sample randomly picked between 0 and 1, okay? And then the probability of picking a number between 0 and 1 is the same for any number I pick, okay? So each time. So that's what I'm doing. I'm picking a number between 0 and 1 in here, and that is assigned to ZA. Now, if, okay, let's continue with this. If ZA is less than 0.5, so I will assume that ZA is about picking A. Okay, so assume that you are on A or on the junction where you're gonna pick A or B. So if you pick A, I'm denoting it with ZA. If you pick A, then number of days that you are going to be spending will be 5 days more. Remember, if you pick A, you're gonna stay 5 days. It's gonna take 5 days for you to get back to where you started. So that is what's happening here. I'm picking a random variable sample here. If it is A, then I'll be spending 5 days, okay? Else, that means if I don't pick A, but I pick B, okay? Then now I'm at B. So when I'm at B, I will pick another random variable, another random sample from uniform distributed random variable. So this time, this is for AB or BB choice. So if ZB is less than 0.5, remember, it is equal probability. It's less than 0.5, greater than 0.5, 50%. So this is the case where I picked AB. Again, I picked first B and then AB. You need to initialize. Yeah, I'm going to initialize, Jeffrey. So I'm going to initialize in a moment. If ZB is less than 0.5, so I'm initializing right here actually. If ZB is less than 0.5, then what I'm gonna do is I'm gonna initialize J in a moment. So I'm going to add 2 days on top of J. And of course, at the beginning, J is 0. So that is what Jeffrey was pointing out. This is the number of days I'm gonna be spending inside the box, J. At first, it is 0. Now, if I pick A, I will spend 5 days more. If I pick B and then that is BA, I'm gonna spend 2 days more. Otherwise, okay, otherwise, so there are 2 otherwises, right? So if I pick A, if I don't pick A, that means I picked B. If I pick BA, 2 more days, otherwise means I pick BB. In that case, I will be spending 1 day more to get to the exit. Okay, so this is what's happening in one loop. Okay, so this is what's going to happen for one case, and then so for one person, I'm going to repeat this procedure for 1,000. That means I will be simulating this 1,000 times. I'm imagining that there are 1,000 miners, or one person is a miner, fell into this situation 1,000 times. Okay, and then each time I'm just simulating how many days for that person to get to the exit. And that is going to be my list. Let's say this is an empty list. And number of days it takes for one person to get outside, I'm going to add it here. So and I will also get outside the while. So the moment I am outside the box, I'm going to append the number of days it took for me to get to the outside, which is J, to my list. Again, my list is keeping each time the number of days it takes for us to get to the exit. And I will repeat this 1,000 times. I hope this part is clear. So let me run this. I hope it's going to run. And it gave an error because here. Okay, so let's see. So my list is 1,000. Again, please do not mix this with number of trials it takes for us to the exit. That's different. This 1,000 is I am repeating this experiment 1,000 times. Each time I'm running the experiment, it is happening here. I'm simulating the whole case. Okay, so the person is at A and B. He picks A, then it's going to take 5 days for him to get back to. And then this while loop is keeping the person inside the box. Okay, as long as ZB is less than 0.5, that means as long as he always chooses, when he's at B, as long as he always chooses BA, he will keep staying inside the box. The moment ZB is greater than 0.5, that means he chose BB, then he's going to leave the box. Okay, this while loop is keeping him inside the box. And then I'm calculating number of days for him to stay in the box. Okay, now let's take the average. Okay, so for that, let's import NP. And then let's just return my list to a NumPy array, and then find the mean. 13 days. Okay, so if I repeat this even more, I think it's going to be closer to 13. But this is enough, right? This is enough to verify what we found at the beginning here, right? So this, we found this mathematically, and we found this using the simulation. Okay, so any questions? Shouldn't J be initialized? Yes, Gayatri. So that was right. So I forgot to initialize J. Now I did. Thank you. Okay, any questions about this? Again, those who are already familiar with coding, this is very simple, right? But if we are new into this, I think it takes some time for us to absorb what is happening here, right? So I hope we are clear about what's happening with this uniform distribution. What is the role of uniform distribution here? Uniform distribution here, this sample we get from the uniform distribution is used for simulating the case where you are making a choice in between two things, right? And then this 0.5 is indicating the probability of choosing one option over the other. If the probability of choosing A was 0.3, I will put it here 0.3. If probability of choosing A is 0.4, I will put it 0.4 in here. Okay, so this 0.5 is the threshold that I'm using to for choosing A over B. Okay, the same thing goes in here. So because in the question it was said that choosing A or B or AB and BB are equal probable, I'm using 0.5. Okay, any questions about what we did so far? I think so. We are saying it is clear, right? It's clear. Okay. Then, if you like, it is tough to understand whether we would be allowed to use the libraries always in the interviews. In this context, would you recommend us to practice without libraries? So here, I cannot think of any interview without allowing you to use SciPy. So any data science interview is definitely will allow you to use SciPy library, but they may not allow you to use maybe. I think last time we saw the question, or maybe in another workshop, but so that there might be a certain function which is directly giving you the answer. So then the interviewer might tell you that, you know what, you cannot use that function because I want to understand actually how you would code that function. But here, I mean, this is so very basic. This is the very basic component of the simulation. So they will allow it. Difference between ZA versus geometric distribution value, ZA versus geometric. So ZA in here is a sample. It's a sample from a binomial distribution. Okay, so I'm sorry, from a uniform distribution. ZA is a sample from, imagine that we have a random variable X, which is uniformly distributed between 0 and 1. So the moment I say this, imagine that we have a random variable X, which is uniformly distributed between 0 and 1. So X, capital X here is representing any number between 0 and 1. And that any number has equal probability for being picked up. So when I say ZA here, ZA is one of the possible values X can take. Okay, one of the possible values X can. So ZA is representing one of the possible values X. Again, capital X is the random variable, which is representing all the numbers between 0 and 1 that may be picked up. So do you have to choose ZA or ZA? So yeah, this is representing. So again, so imagine that this is a number line. On the left of the number line, we have 0. On the right of the number line, we have 1. Okay, so imagine that we have a number line between 0 and 1. And between 0 and 1, it is equally probable for us to pick anything. Okay, anything. Now I am picking ZA. Let's say ZA is right here. ZA. Now, from 0 to ZA and from ZA to 1, it is representing, so the distance from 0 to ZA is representing some percentage of this. If from 0 to 1 is 100%, from 0 to ZA is ZA percentage. Okay, so if, let's say, picking head is, so what is the probability of head? Let's write it that way. Probability of head. I'm referring to an example of flipping a coin, and probability of head is 0.7, and you want to simulate this. So what you're gonna do is you're gonna pick a number ZA between 0 and 1, and then you're going to look the location of ZA. So if ZA is, let's say, you picked a number which is 0.6. Okay, you picked a number which is 0.6. So that means to the left of 0.6, it is 60% of this interval from 0 to 1. To the right of 0.6, it is 40% of the interval between 0 and 1, right? So you already divided 0, 1 interval into two pieces, 60% and 40%. So probability of head is 0.7. That, what you can do is anything, so from 0, if I say to 0.7, 1. Sorry for this. Maybe I may be spending more time, but I think this is important. This part is important to understand what's going on. And then let me make this a little bit more realistic, 0.4. Okay, so 0.7 is probability of head. I'm placing 0.7. This is the threshold for head. So anything below 0.7 is 70% of this whole interval. So what I'm gonna do is, if I pick any number from 0 to 0.7, right, it is coming from the 70% of the interval between 0 and 1. So that's why the number I pick, if it is 0.4, which is less than 0.7, so it is coming from this 70% interval of 0 and 1. So then I'm going to assume that I picked head in this case. If 0.4 is less than, which is 0.4 is my ZA, is less than 0.7, right? I assume I picked head, because 0.4, which is ZA, the number I picked between 0 and 1, it is coming from this 70% interval, right? And that 70% is representing the probability of head. I hope that I was able to answer the question. This is important to understand why we are using uniform distributions to simulate this binary choice. Okay, so if it is all right, let us go to the next question. So geometric distribution is like flipping a coin trial. Yes, until you find the first head, or until you find the first tail. Okay, so let's look at this problem now. Let's say you flip a fair coin. Again, the person immediately gives you that the probability of tail or head is 0.5. It's equal probability. Fair coin, that's what it means. So let's say you flip a coin, fair coin 10 times. What is the probability that you only get 3 tails? So what is the probability that you only get 3 tails, but all the tails happen consecutively? So there is a condition here. So there are going to be 3 tails, and all of them will happen consecutively. That means tail, tail, tail. So here is the example, right? Head, 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 and then tail. If you have this head, 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 tail, tail, head, tail. So and then head, head, head. So this is not counted because 3 tails are not consecutive. So let's now go back to question. What is the probability that, so you are flipping the coin 10 times. What is the probability that you only get 3 tails? That means you get 7 head, and the tails have to happen consecutively. Okay. So at first this question, like, it sounds like, oh, it's too much to think about, right? But if you think a little bit carefully, right, a little bit carefully about the question, actually, we have limited number of cases where we can get 3 tails consecutively, right? So let's say this is one of those rare cases. So I start first tail, 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 and then head, 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 head. Well, how many? 4, 5, 6, 7. Okay, this is one of the cases. Then head, and then tail, 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 and then head, 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 right? This is another case. Actually, but if I shift those 3 tails as a window, so I don't have too many cases, right? So how many cases do I have where I have 3 tails consecutively? Sorry, I missed Ramia's question. So ZA represents, yes, ZA is representing probability. Sorry for missing the question. So let me ask the question one more time. If I shift 3 tails as a window, and remember I have 10 positions and 3 tails are shifting, how many different cases I'm gonna have? Is it 7? Is it 7 or 8? How many do you think? Okay, so let's have a consensus. So I have 2 7s and 2 8s. So let's see. So I have, let's imagine that this 3 is a single number. Let's imagine this 3 is a single number. Then how many positions I have now? So imagine, so I have 7 heads and 1 block, right? So I have 8 positions. And then that block can take 8 different positions, right? That means I have 8 different cases where I can have 3 tails consecutively out of 10 flips of a fair coin. Is this clear? Is this part clear? I'm just assuming that 3 tails is 1 block. Then I have only 8 positions. So then this block can be positioned in any of the 8 positions. That means I have 8 different cases where I have tails, 3 tails coming consecutively. I hope this part is clear. Okay, that means out of all the possible flipping the coins 10 times, out of all the possible, by the way, how many possible cases do I have? If I flip a coin, how many different head and tail combinations can I create if I flip the coin 10 times? Right? So again, I have 10 positions. Each position can take either head or tail, and I have 10 of them. So the first one can take 2. The second one can take 2. So Sanskriti already gave the answer. So I have 10 positions. Each position can take either head or tail. That means I have 2 to the power of 10 different combinations of head and tail. Thank you, Jeffrey. Okay, so again, let's go back to the question. What is the probability that you only get 3 tails, but all the tails have been consecutively, and then we are flipping a coin 10 times? Out of all the positions, which is 2 to the power of 10, I'm only looking for 8 combinations, specific combinations. So the probability is 8 over 2 to the power of 10. That is the answer, right? That is the answer. So out of all the different combinations of head and tail, we have only 8 cases where I can have 3 tails consecutively coming, right? It's a very small probability, actually, if you think about it. Okay, so that was the 4th question, but I was thinking about maybe we can simulate this. Okay, let's try to simulate this. Actually, simulating this, I'm going to do this in 2 ways. I'm going to do this in 2 ways. Again, going back to one of our friends asked, what if the interviewer doesn't allow us to use a certain function or library? I think this can be an example to that. For example, if the interviewer allows me to use combinatorial, so combination from math library, the answer to this question is actually extremely simple. Right? So how can I solve this? Let me actually, this question is, I mean, it's very, what is that? Simple, but let me ask you another question, which is going to be a different version of this, and then try to simulate, because this one is going to be easy when we solve the other question too. Okay, I'm asking you another similar question. Okay, so let's assume, say we have 6 green. Q1 and Q2, we had them last time. If you again, I'm gonna give this whole what is that thing, notebook to you. If you could please give us a review. Okay, that is what my friends told me, so I'm telling you. If you could please let us know about your review. So I'm gonna share this notebook with you. Okay, 1 second, please. I'm confused here. Okay, let's say we have 6 green, okay, and 4 blue, what is that, cards. Okay, let's say we have 6 green and 4 blue cards. I'm just making up a question here, okay? And then yeah, so I'm making up a question, Jeffrey, which is similar to this one. It's a little bit more difficult than that one. And then I will try to solve this problem with some simulation. Okay, let's say we have 6 green and 4 blue cards. Each time you will pick a card, okay? Each time you will pick a card, and picking a blue or green is equal probable, okay? It has equal probability. I think it is easier to say that, which is 0.5, right? So picking blue or green has equal probability, which is 0.5. And the rule is whichever color remains at the end. Okay, so you keep picking a what is that card without replacement. Let me also add that you will pick a card without replacement. Let me also add that one, without replacement, and then whichever color remains at the end, okay, that color wins. Okay, so let's say this is some game we are playing. Okay, so there are 6 green and 4 blue cards. Each time you pick a card without replacement, picking a blue or green has equal probability. Whichever color remains at the end, that color wins. All right, so that is the rule for the game. So what is the probability that green wins? What is the probability that green wins? Okay, so let's think about this. All right, so it sounds simple. It may not be very simple. All right, but it is related to what we did earlier, but a different version. We need to think a little bit careful in here. All right, and how can we solve this problem? We can solve it first mathematically and then do some simulation on that. How can I solve this problem? If there are 6 green and 4 blue, then picking either does not have equal probability. Picking either has equal probability. I see what you are saying. So I see what you are saying. So if there are 6 green and 4 blue, then picking either does not have equal probability. Let me. So what I'm trying to say is that is right. It's going to make it yeah. So let's without replacement. Let me just delete this one, because this is not right, as Jeffrey pointed out. Picking a blue or green does not have equal probability if we have 6 green and 4 blue cards, and then this is happening without replacement. Each time I pick a card, we have the remaining number of cards is changing, and of course the probability will not be the same. Yeah. So let me take this back. So thank you for the reminder. Let me take this back, and then let's think one more time about this problem. So we have 6 green and 4 blue cards, and then we are picking a card without replacement, and then whichever color remains at the end, that color is going to win. So what is the probability that green wins? How can we solve this problem, right? Let me see if. So if you think, so there are different ways maybe we can approach it. You can say first you have 6 green and 6 blue. Yeah, so we have 6 green. Oh, so you have 6. Yeah, but then again, when you pick, let's say it depends, right? So if I have 6 green and 6 blue, if I pick green and without replacement, then again, the probabilities will change. So that's why I took it back. So in my mind, I had a different question, so I take it back, okay? So then how are we going to solve this problem, right? I mean, there are different ways we can approach the problem, but let me make your job easy, okay? I'm gonna make one suggestion, and then I think this is gonna make your job easy. Again, If this was an interview, maybe maybe this, you can consider this as one of the hints. All right. So because at the end, if we want the green to win at the end, so that means we are considering all the cases where the last card is green. Okay, we are considering. Imagine, so the confusion here is, so when I first heard this problem, I was also approached this problem from that angle, and then I think that angle is not the easy way. Is that we are imagining that we are going to pick a card, put it aside, and then pick another card, put it aside. So let's imagine that there are 6 green and 4 blue, and then you are considering all different combinations of 6 and green and 4 blue, all different combinations, and then consider only the ones that where green is the last one. So let me put it here. Let's say you have green, 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 right? It is 5 greens. So the moment I put these 5 greens, so let's say these are indicating the order in which the person picked, right? So he picked first green, and then again green, and then again green. The moment this happened, the game is lost for green, because all the remaining ones are blues. So I will only consider the case, no matter what happens in the first 9 cases, I will only consider, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are indicating green and blues picked by the person, no matter what happened in the first 9 cases. If the last one is green, I will always win. The green will always win. So that means, so just think about it. Think about it. Let's say the person picked blue, 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 blue. The moment this happened, the green wins the game. For this case, we know that at the end we have green. Let's say the person picked blue, then green, then blue, then green, then green, then green, then blue. So 3 blues, right? And then let's pick another blue. The moment this happened, again, we know that the last one is green, right? So any case where green wins, the last one is green. That we need to consider the cases where the last one is green. Then let me ask you this question. How many different cases do we have where the last one is green? Any suggestions? The probability that green will be lost is the same as if the green is picked first. That is 0.6. Why is that? Green is the loss is the same as if the green is picked first. So how many different cases can we have where green is the last one? So it's actually easy, right? So the last one is fixed. The last one is green. I fixed that one. Then how many positions left? There are 9 positions left, right? There are 9 positions left. So again, here, right? I fixed the last one. I know that it is green. When I fix this, then I have 9 positions. Now I'm going to distribute these 9 positions across 5 greens and 4 blues. Okay, across 5 greens and 4 blues, I have 9 cards. Okay, I have 9 cards. Out of these 9 cards, if I place greens, if I place the 5 greens wherever they want, okay, if I place them wherever they want out of these 9 positions, the rest will be blue. That means if the last one is fixed as green, the total number of cases where I have the last one as green is combination of 9 with 5. Right? Again, I fixed the last one as green. I have 9 positions left. Out of these 9 positions, the remaining 5 greens, I can put them wherever I want. By the way, 9 with 5 is the same with 9 with 4. So I can either place the remaining 5 greens or the remaining 4 blues. They will give me the same result. All right. So I place the remaining 5 greens across 9 positions. So wherever I put green, wherever I don't put any green, I can place blue, right? So this is total number of cases where green is the last one. Then I can divide this by total number of cases, right? So what is the total number of cases if I have 6 green and 4 blue? So again, I have 10 positions. if I can place 6 greens across these 10 positions, the remaining 4 will be blue, right? So then 10 with 6, right? Combination of 10 with 6. This is the total number of different combinations of 6 green and 4 blue. And out of these, I have cases where the last one is green, and these are the ones which actually wins the game. All right, now let's solve this problem. Import math. I'm going to use math combination of 9 by 5. Okay, divided by math combination and with 6. Well, we can do this, solve this problem this way. Let me also try to solve. I know that we are out of time, but let me solve this problem with another simulation very quickly. For this one, I'm going to use permutations. Okay, permutations library from iteration tools, import permutations. Okay, so I'm just now going to be solving this problem a little bit more explicitly. So here is the cards. Okay, I'm just explicitly assigning the cards. Okay, just bear with me. This is green. And then let me just copy this. Okay. Okay, so this is the first green, and then second one, third one, fourth one, fifth one. I'm sorry, 1, 2, 3, 4, 5, 6. Okay, the rest are blue. Okay, I like doing simulations because things are becoming much more clearer. Okay, now what I'm gonna do is, so these are the cards. What I'm gonna do is I'm going to create all the different combinations of yeah. So let me think what you suggested, Jeffrey, because you gave the correct answer. Let me think what you suggested, okay, after this class. So I'm gonna find all the different combinations of cards. Okay, so if I'm given this 6 green and 4 blue, how many different ways can I put these cards? Okay, so here's what I'm gonna do is combinations is list of all the permutations of, okay, my cards in 10 positions. Okay, so length of combination. So I have this many different combinations. Again, if you look at combination, the first 10, look, as you said, the first 10 are the same, right? Yeah, the first 10 is the same, right? Because I mean, here the permutation is assuming that this green is different than the second green, but they are the same, right? They are the same. But I have this many combinations. Okay, now I would like to see the last one, if the last one is green or not. So that's what I want to do now. So let's just create a for loop. Let's see, for T in combination. Okay, I'm gonna pick each one of these separately, and then I'm gonna check the last one. Okay, if the last one is green. Okay, I'm just counting the cases where the last one is green. Okay, and then I'm just gonna keep that green here. So that I mean, there are different ways you can do this, but I will just do it this way. So this is gonna keep the list of all the greens where the last one is green. Okay, so these are the winning combinations. Winning combinations. Okay, let's put this, and then it gave an error. T is not defined because for not IT. Okay, now I'm just going to divide length of the winning combinations. Okay, winning combinations by the length of the combinations, which is 0.6. Again, it's a very simple simulation, but at least in my mind, it's very clear what is happening here. So the person can pick green and then green, but each of these greens are in this case considered as different because these are different cards. Okay, or I pick this time this card first and then this card second, right? It looks like the same greens, but this is the second card, this is the first card, right? So let me stop here. I think I'm out of time. Let me stop it. I was thinking to have another problem, but maybe we can do this the next time. My goal is trying to first give the solution as much as I can, and then try to simulate it. So that's my goal. Hopefully, in our next meeting, I am going to solve a couple of more problems. And again, as I said in my list, I'm planning to have some other topics too. For example, A/B testing is one topic that I want to definitely address. Hypothesis testing is another topic that I want to address. So I'll try to solve some interview questions on these topics later on. Thank you very much for listening, and thank you for your answers and then comments. So I'm going to share, as I said, this notebook with my friends at Magnimind, and then if you could please send an email back to them with your posting review, so they're going to share this notebook with you. Thank you for listening. I'll see you guys next time. Take care.